Dear students, welcome to the knowledge series. Here we are going to see the discussions on shortest path. We will be initially discussing on Dijkstra algorithms and later on Bellman-Ford algorithms in a different video series. What exactly the shortest path it means? To understand this shortest path, here a certain example is being shown. As you can see here, there are three different nodes that is being shown over here. That is a node U, T, U and V. These are the three nodes which we consider as a vertex. This is a starting vertex. This is a destinations or the end vertex we can consider. Every starting vertex is having its own weight as 0, and the link, that is the distance from T to T itself, is also 0. That is we consider as a default. The shortest path or the shortest distance, it is important in the various different applications. The reason is that the time we spend for the packets or the information or the data that has to transfer from a particular node to the destination node, if it is following a shortest path, then the utilizations, we can put it as the utilizations of the network can improve. That is one factors, and also the efficiency over which the particular algorithms or the particular system is working, it can improvise. So that's why we follow this shortest path study. As I have stated to you, is that the starting vertex has its own weight. This we consider as weight. The own weight at the starting point is 0. Similarly, the other nodes also will have its own weight. Here one important thing we have to understand is that between T and U there is a unit that we consider as a link cost, or as the edge cost. If the node is directly peer-to-peer connections, that is a direct connections, then we consider its weight will be corresponds to the cost of the link plus the previous node's weight. That is what. But if the node if the two node which is connecting through a intermediate nodes, that means here T to V, if these two nodes are connecting through a intermediate nodes, then that is the U, then its link cost will be different. But if we consider T to V as a one path which is not a direct path but an indirect path, then under that situations we will consider the weight of the destination node will be infinity. That is what you can see here. T to U, it's a direct path. That's why its weight is corresponding to the weight of the previous node plus cost. That means T to U will be the weight of the previous node is T is equal to 0, that is 0, plus between T and V the link cost is 5, that is between T and V. Then under T and U, under that particular situations, 0 plus 5 is equal to 5. So what is this 5 indicates? This is the new weight at U. That is what we say here with respect to these particular situations. But between T and V, it's an indirect path. There is no intermediate nodes. So, and which is directly connected between connecting, not directly, indirectly connecting between T and V. So, because of this indirect path, we always consider the initial weight as infinity at the destination set. That's why it is infinity. Now, if we consider under these particular situations, then this gives us certain steps to understand that how the Dijkstra algorithm works. So, we will consider this figure for the Dijkstra algorithms to understand. Before that, let me also point to you is that once we start from T and we move to U, based on the cost of the link between T and U as phi, then we get the new weight as also phi. So this is the weight at U. But U to V, if you consider, what is U to V? U to V, if you consider the new path U to V, under these conditions, we will consider the weight of U plus the link cost between U and V. What is the weight of U? Is 5 plus the link cost is 3. That is nothing but 8. So that is the new weight it has generated. So this is 8 and this is infinity. So decisions need to take place between these two. That decisions what we termed as a relaxations condition. That segment we will see below. Here we are going to discuss Dijkstra shortest path. Dear students, you can see again here there is a 3 nodes T, U and V. The same node is there where what is this one? This is termed as weight and this is termed as cost between T and U. That is the link cost or the edge cost. So here what is the initial weight? 0. So between T and U, if you are considering the distance from the starting point T to the end point, final end point is nothing but V. So between T and U, the distance is equal to T is having its weight 0 plus the link cost is 5. So that gives 0 plus 5 as 5. On the other hand, if you see T to V, the distance is how much? The distance is equal to infinity. That is what we have discussed earlier. So starting distance of the T here, and this is the distance between, this is the weight at U, this is the weight at V, and this is the weight at 0. Now we are going to see the relaxation condition. What is this relaxation conditions it means? Now here if you see it states that if d of u, that is the weight at u, plus cuv, that is the link cost between u and v, if this sum is less than the weight at v, then under that conditions we have to do a modification, or we have to do a relaxation condition based on the relaxation condition satisfactions. If this condition exists, that indicates that relaxation condition is satisfied. Then we have to update the d of v, the previous d of v with the new d of v. So what is the d of v? D of v is equal to d of u plus c u of v. If this conditions satisfies, then only we can modify. So here you can see, check the relaxations conditions. Now what is this relaxation condition? D of u is 5. That is the weight. What is the cost between u and v? It is 3. So automatically you can see the weight of u plus link cost between u and v 3. That is, we are getting a new weight at V as 8, and 8 is less than the previous weight at V. What is this one? This is, we can put it as d of V, d of V. So d of V was infinity. So since this condition, relaxation condition satisfies, then we update or modify this one with the new weight. So updated weight at V is what? Infinity. It has switched over to 8. So this is the new weight at V. So this is what we is termed as a Dijkstra algorithms. Here one more point I would like to add, dear students, for your understanding, is this one. Just like Dijkstra algorithms, there is another algorithms we will be discussing later on, that is Bellman-Ford algorithms. Only the just hint purpose, what I would like to say is that in the Bellman-Ford algorithm, all other node, I can put it as all other node except the starting node, that is the initial node, the weight is considered as infinity with respect to the starting node. That means if here in this figure, if we consider t is equal to 0, then you will be having a weight infinity, we will be having a weight infinity, and the source node itself will having its own distance 0. So this completes our basic understanding of Dijkstra shortest path algorithms. Thank you.